Let's look at some examples. First question asks us to find the pH of some solutions. And what we need to do is determine which formula will be appropriate for finding the pH. And in some cases, it will require two steps and using two formulas in order to do so. The first question gives us the concentration of the H3O+. So therefore, we can plug directly into the pH formula, which is that the pH is equal to the negative log of the concentration of the H3O+. And when we use our calculator to do that, we find that we obtain 1.810. Now, when doing pH calculations, one of the things to note is what's a little bit interesting about significant digits and pH values. What we need to recognize is that the number in front of the decimal place is actually giving us the power of the concentration. So it's giving us the range of 10 to the negative 1 to 10 to the negative 2 in terms of the concentration. Because it's just basically telling us the exponent on the power of 10, it's not really a significant digit. If we think of the number as being in scientific notation, 1.55 times 10 to the negative 2, you know that this value is not associated with the significant digits. And this is connecting us to the fact that we have a pH of 1. It is these digits here that are the significant digits, as you know from reading values in scientific notation. And these ones are the ones that will change the decimal point of the pH value that we have. So when you're recording pH, it's the decimal points that are actually the significant digits. So if we want 3 significant digits, then we need 3 decimal points. For the most part, because most pH meters read to 2 decimal places, you'll find that a lot of times people will simply report their answers to 2 decimal places and not worry too much about the significant digits. This next example, we have the concentration of the OH-. So we can't find the pH directly, but we can find the pOH first. So the pOH of this solution is 1.64. And to find the pH of the solution, we're going to take 14 and subtract the 1.64, and we're left with 12.35. Now, I really encourage you, because part of doing these problems is the use of your calculator, I do encourage you to do the calculations along with me so that you can make sure you know how to use your calculator. So what you might notice right after my discussion that I've reported this to 2 decimal places, which is pretty standard and within reason for significant digits. This last example, we're given the pOH, so we simply report the pH by subtracting the 10.12 from 14, and we're left with 3.88. And as you know, when you subtract 2 numbers, you follow the decimal place rule. So this is reported to the appropriate number of significant digits. In example 2, we're given the pH of 4.82, and we're asked to find the H+ concentration of a sample of rainwater. When you've got the pH, the concentration of the H3O+, or H+, which as we've discussed as being interchangeable, is calculated as 10 to the power of negative pH. And the answer is 1.5 times 10 to the negative 5. This pH has 2 significant digits, as does my final answer. Now, pH does not have any units, so what we need to do when we're studying acid-base chemistry is remember that although pH doesn't have units, the concentration of the H+ is going to be reported in moles per liter. So we need to be mindful and not forget about our units for our concentration. This last example, we've got the concentration of the hydroxide ion in the solution, and we want to know what the pH of this sample of blood is. Now this is similar to example B, but I just want to show you that there are two ways to solve for the pH when you are given the concentration of hydroxide. In the example above, we found the pOH, and then we subtracted from 14 to find the pH. And in this case, we'll use another relationship that we have, which is that the concentration of H plus times the concentration of OH minus is always equal to 1 times 10 to the negative 14. So the concentration of H plus in this case is going to be 1 times 10 to the negative 14 divided by the concentration of the hydroxide, which is 2.5 times 10 to the negative 7. And we find the concentration of H plus is 4 times 10 to the negative 8. Now you do need to be careful when you're using your calculator to do this calculation. You want to properly enter the numbers in scientific notation so that you don't have an order of operation problem and you end up with an incorrect answer. Now you can also, by inspection, observe that these values make sense because the concentrations, the exponents, will always add up to negative 14. Okay, so based on these values, it makes sense I'm adding up to negative 15, which is in the proper range. If, for example, you got a sum of negative 23 or positive 22, then that wouldn't make sense and you would want to go back and make sure that you've done the calculation correctly. Now that I've got the concentration of the H plus in the solution, I can find the pH by taking the negative log of this value, and I find that I've got a pH of 7.40, properly reported to 2 significant digits. Now we're going to have one more discussion about a point of theory in acids and bases, and then we're going to do calculations that are directly associated with strong acids and bases. What we're looking at is what is called the strength of acids and bases. And the strength of an acid or base is actually a property. It's not something that you can change, and it's not to be confused with the concentration of the solution. When we talk about something being strong, we're not referring to the concentration of the solution being a high concentration. In fact, you can have a very weak acid that is of a very high concentration. So these are two very different concepts. The strength of an acid is related to the extent at which the acid or base can ionize in solution. When we look at strong acids, they completely dissociate in water. So what that means is that every molecule of HCl that I put into solution will dissociate and break up into H plus and Cl minus. Okay, so this is a good visual here. If I put 100 molecules of HCl into the solution, I can expect that all 100 of them will dissociate, and I'll be left with 100 H plus ions and 100 chlorine ions in the solution. Now there are only actually 6 acids that are considered to be strong. We refer to them as the big 6, and it's really important as you proceed in your studies of chemistry that you know and can recognize which acids are considered strong acids. The strength of the acid is related to the strength of the bond. So these bonds are more easily broken than in other cases. Hence, they're able to dissociate quite easily in solution. So we've got HCl, HBr, and HI. And we've got nitric acid, which is HNO3, sulfuric acid, and chloric acid. Now the strong bases also completely dissociate in water. And the strong bases are identified by the soluble hydroxides. So if you look at the periodic table and you look from lithium downwards, and then you look from calcium downwards on the periodic table, what you can see forming is what I refer to as the big little b. So it looks like a lowercase b. And these are soluble hydroxides. So if you look back at your solubility rules, these are the hydroxides that are soluble in water. And being soluble, they will completely dissociate. So for every 100 sodium hydroxides I put into solution, I will dissociate to produce 100 sodium ions and 100 hydroxide ions. The opposite to this is a weak acid, or a weak base, and these will only partially dissociate in water. Weak acids tend to be our organic acids and can be recognized with the carboxyl group, and weak bases tend to be our amines or derivatives of the NH3, which we've previously discussed. These are the ones that we use this funny new arrow, which is our equilibrium arrow, in order to explain. And it's because the reaction doesn't go to completion. All of the reactants that are available don't completely produce products. Only some of them will dissociate. So as a visual here, if I've got this weak acid of HF, if I put 100 molecules of HF into solution, 95 of them might stay intact as HF in the solution, producing only 5 H plus and 5 F minus in solution. So this would be a 5% dissociation. Only 5% of the molecules that I start with actually dissociate to produce products. This is going to affect the pH of the solution relative to a strong acid. And this is something that we spend a lot of time in grade 12 studying. Our focus this year is going to be on strong acids and bases. For now, understanding the difference and being able to recognize that you have a strong acid or a strong base versus a weak acid or base is what we'll need to be able to do. Now, when we want to find the pH of strong acids and bases, we're going to be using the same formulas that we've previously looked at, but we're just going to do some preliminary information in order to identify the concentrations of the hydronium or hydroxide ions in solution. With an acid that completely dissociates, what we'll see is that the concentration of H plus is going to be equal to the concentration of the acid in solution, because as you can see, they dissociate in a 1-to-1 ratio. For bases, if they dissociated in 1-to-1 ratio, then the hydroxide concentration will be equal to the concentration of the base. But if they don't dissociate in a 1-to-1 ratio, then we'll need to consider the ratio that they've dissociated. Let's do some examples to see how this works. We've got an HBr solution that is 0.148 molar, and we want to know the pH and the hydroxide concentration. So the HBr we recognize from the list as being a strong acid, meaning that it will dissociate completely into H plus and OH minus. Sorry, Br minus. Now the concentration of the HBr in the solution is 0.148, and so what that means is that when this dissociates, the concentration of the H plus will also be 0.148. For every 100 of these, I put 100 of these in the solution, so the concentration of the H plus is equal to the concentration of the acid. From this, I can find the pH of the solution by subbing into the formula. pH is equal to the negative log of the concentration of H plus, and I find that the pH is 0.829. To figure out the concentration of the hydroxide, what I can do is simply plug into my formula, which is 1 times 10 to the negative 14, divided by 0.148. And we'll obtain the concentration of the hydroxide. Number 2, it asks us to find the pH of a sodium hydroxide solution. So this is a base, so I'm going to expect the pH of this solution to be greater than 7. And that's something that you should think about when you encounter a solution so that you can check your answer at the end. This is one of my strong bases, so I know it dissociates completely in solution. And so the concentration of the hydroxide here is 0.0425 because it's in a 1-to-1 ratio with the sodium hydroxide. For every one of these I have in solution, I have one hydroxide ion, so the concentration is the same. I've got the hydroxide concentration this time, so I can't find the pH directly. I can find the pOH first, and then subtract from 14 to find the pH to be 12.63. This next example, I've got calcium hydroxide. And calcium hydroxide is a strong base. It's one of my soluble hydroxides, and when it dissociates, it produces one calcium ion and two hydroxide ions. Now the concentration of the base is 0.0425, and to figure out the pH, I need to figure out what the concentration of hydroxide is in this solution. Because the calcium hydroxide and the hydroxide are in a 1-to-2 ratio, what that means is that the concentration of the hydroxide in this case is actually going to be twice that of the calcium hydroxide, which is 0.085. So it's double the concentration. Once I know that information, I can find the pOH, which is 1.70, and the pH, which is 12.93. And let's look at one more problem. What mass of HCl is needed to prepare 350 milliliters of a solution that is of pH 1.1? So in this case, I know the volume of my solution, and I know the goal pH of the solution, and I want to know my mass. So I'm actually going to need to do 3 steps to solve this. I know that my mass will be equal to whatever the moles I need for my solution is, times the molar mass. And I know to find the moles, I'm going to need to multiply the concentration of the solution that I want times the volume. So really, what I need to do is figure out the concentration of the solution first, which I'm going to do by finding the hydronium ion concentration from the pH. So my first step here is to use my formula to find the H+ concentration, which is found by taking 10 to the negative pH. And what I find is that the concentration that I need of the H+ is going to be 0.0794 moles per liter. Because I'm working with a strong acid, working backwards from that concept, I know the concentration of H+ is 0.0794. So that means that the concentration of the HCl is also equal to 0.0794 because they exist in a 1-to-1 ratio. Now that I know the concentration, I can use my previously discussed formulas in order to find the mass. So I'll find my moles by multiplying the concentration of 0.0794 times the volume, remembering that the volume needs to be in liters, so I'm going to multiply by 0.35. So the moles that I need for this solution is 0.0278. And then the mass I'm going to find by multiplying by the molar mass. This is the moles of the HCl that I need to make the solution. So I'm going to find the molar mass of HCl, which is 36.46. I'm going to multiply by 0.0278, and I find that I need 1 gram. And to be true to my significant digits, I only have 1 significant digit, so I'm only going to report my answer to 1 significant digit. So this includes our lesson in acids and bases.